Yeah, hope you all can hear me. I thank the organizers for this opportunity to present my work. So I'll be talking about the nature of the persistent radio source associated with one of the well-studied repeating events, the second known repeater. So over the past few days, we have all talked about a lot about FRBs. So I just thought I'll summarize some things here. So I might go a little quicker here. So yeah, the origin of FRBs is still an open question. There are different models that have been proposed. There are a cartoon of a few of the models here. There are very exotic models like this to explain some of the repeating FRBs. There are some models which talk about mergers, and if so, the observations of FRBs itself have given us these kind of sources. So there are repeaters and there are apparently one-off events. We don't know if these one-off events will repeat later in the future. So if so there is this question of if there are actually different populations. So if there are separate one-off events, then mergers can also cause them because these are catastrophic events. Again, there's this question of if there are different progenitor mechanisms itself for within each of these populations or as the FRB population as a whole. So there is this catalog of the possible models here called FRB theory cat. So you can just go there and look at it. There are a lot of different models. So to understand what FRBs are, we have again talked about this in the last few days. So I just thought I'll break this down into two things. So to understand FRBs, we need to localize them and then we need to follow up. So to localize them, we have already seen that there are new instruments, new commensal systems that are looking for FRBs and trying to localize them to smaller regions in the sky. Once we have them localized, then we can think about looking at the electromagnetic signatures from these events. So we can look at the environments in which they are, look at the intervening medium between them and us, and then try to understand what causes these FRBs. So we have also talked about, there were very good talks about host studies. So yeah, looking at where these sources are within the host galaxy can give us some idea about what they are. Again, we have to look for counterparts. So if we have really good localizations, we can start cross-matching with other known transients or other wavelength surveys to look for any counterpart emission that could come from these sources. We know only, I think, one such event of the galactic magnetar, which showed X-ray bursts along with the FRB-like bursts. Then we can look at this thing called persistent emission. So what is this persistent emission? I'll just go to that. So some of these FRBs, a very, very small fraction of these FRBs have been seen to show persistent radio emission. So I'll just get to that in 1 second, but by handful, I mean 5 of them. So there is one very recently discovered one, which is in Alexander's paper, which came out very recently. So I suggest all of you to just look at this paper. It's a very nice paper which gives our current understanding of all PRSs and FRBs in general. So it's a nice paper to look at. So this is they reported the discovery of a persistent radio source which is associated with this particular FRB. So there are five FRBs which have been shown to show this persistent radio emission. All of these are repeating FRBs. So again, we don't know if the apparently one-off events actually have any persistent radio emission. What we mean by persistent radio emission is continuous radio emission. On top of the burst-like emission that we see from these repeaters, we also see a continuum radio emission which is active for a very long period of time. So many of these have been studied for a long time. So if you see 121102, the first repeater that was discovered, it has been the repeating bursts have been studied for a very long time, and we have observations of the persistent radio emission for the last 6, 7, 8 years. Then we have 190520, also which has observations for the last five years. The persistent radio emission has observations for the last 5 years. So the characteristic of these persistent radio sources is that they are really bright in the radio. You can see the radio luminosities here. They also have a very shallow spectral index. So you can look at the spectral index that is above these frequency bands that are listed here. Then all of these persistent radio sources also had EVN observations to actually localize them better. So the EVN campaigns were also to localize the bursts. So we have strong constraints on the physical size of almost all of these persistent radio sources. We also have constraints on the offset between the distance between the locations of the bursts and the persistent radio emission itself. So except for this one persistent radio source, most of these persistent radio sources have very small physical size, and they are also very, very close to the FRBs that the burst source itself. So this actually gives us an idea about the possibility that the persistent radio emission and the burst emission are coming from the same physical source, or from the immediate vicinity of the physical source that is producing the burst itself. So given the persistent radio emission for these, I'll just discuss a few possible models that have been used to describe both the burst and the persistent emission. I mean, this is not an exhaustive list. I'm just trying to give an idea of some of the models. So the first model here, given the detection of the X-ray and X-ray bursts and the FRB-like emission from the galactic magnetar, we know that at least some FRBs may originate from magnetars itself. So there is this model called the magnetar wind nebula. So where after a massive star undergoes supernova, there is a supernova ejecta, and it leaves behind an active magnetar. The activity of this magnetar actually inflates a nebula within the supernova ejecta itself. The FRB comes from the shock of the shocks that generate the activity, whereas the persistent radio emission comes from the nebula here. So there are electrons here in the magnetic field which are producing the persistent radio emission. We see the RM itself, the change in the rotation measure, also due to the ions present here in the ions and the magnetic field present here in the nebula, and the DM itself comes from the ISM and the medium towards us. So this is one model. There is another model called the hypernebula model, where we have a compact object which is accreting onto itself from another companion. The companion is not shown here. The accretion itself might cause production of FRB-like emission from the source, whereas it also starts to emit a wind-like emission from a slow wind-like emission, which will interact with the interstellar medium and start producing the persistent emission that we are seeing. So yeah, these are the two major models that we actually talk about when we are looking at persistent radio sources. There are other models also, but now I'll just go on to talk about the persistent radio source that of interest that I'm going to talk about right now. So FRB190520 was actually discovered by FAST and was localized to a dwarf high star forming galaxy. This FRB itself also had EVN observations, VLBI observations, which actually showed the presence of a compact PRS. So this is the image of the persistent radio source. The spectrum for the PRS actually resembled 121102 at frequencies greater than 1 gigahertz. There were lack of low frequency observations of this source. So what we did is we compiled long-term both UGMRT and VLA data to study both temporal and spectral evolution of the source. So just before I go to our data, up to 2021, this source was also extensively studied by other groups with VLA. So this is a plot of the spectrum. The different colors here are the different epochs. So in this study by Zhang, they have actually shown that from the 2020 epoch to the 2021 epoch, they had seen a slow overall decay in the flux in all frequency bands. So what we did was we took GMRT and VLA observations along with some of the archival observations for this persistent radio source, and we compiled them here up to 4 years after its first observation. So what we see here, the main thing that we have to see here is the light blue color, this one, which is 1.5 gigahertz, which combines both VLA and GMRT observations. We do see some evidence of the source brightening and dimming on timescales of like a week here. I'll talk about that a little later. So to look if there are trends, monotonic trends in the data itself, what I did was that I scaled all the data to 1.5 gigahertz using a spectral index, changing the spectral index to, I used the spectral index here at the end of 2021 epoch, but changing that to any of the other values doesn't change it much. So if we do a statistical test for monotonic trends called the Maan-Kendall test, I won't go into the details, but it tells us if there are if there's a monotonic decrease, increase, or no change in the in a data set. So we did find a decreasing trend, and I show the linear regression that shows a decreasing trend here. There is, however, this brightening and dimming, which I'll just talk about in like 2 or 3 slides from now. So yeah, given the dimming, what we did was we tried to look at any physical constraints that we could try and obtain. So the magnetar wind nebula model that I talked about, we tried to give a joint, make a joint time and frequency fit for all the data that we have till now. And so here I'm just showing the time, the light curve as a function, the flux density as a function of time, and for the different colors are the different frequencies. So this is the joint fit of the magnetar wind nebula model. So given the magnetar wind nebula model, we can actually get constraints on the age of the magnetar, the energy injection from the magnetar itself, the rate of energy injection from the magnetar. So yeah, we were able to actually constrain the age of the magnetar to around 52 years. This is slightly higher than the estimates from the other fits till now, but it still sits within the allowed parameter space. I'll just come to the parameter space in a second. For the hypernebula model itself, there were already fits from previous studies, and at these timescales and from the observations of the bursts itself. So the hypernebula model actually predicts some variation in the DM of the bursts itself over time. There are slightly contrasting things about this source. So there have been studies of DM of the bursts itself, and initially it seems to be showing not enough variation, but there are also some studies which have shown a slow decrease in the DM over time. For the spectral fit itself, so the same joint fit that we did in the previous slide, I've shown here on the spectrum though. And the different colors here now represent the different epochs. So what we can pay attention to here is the GMRT low frequency data, the data that is below 1.5 gigahertz. So we didn't have many observations of this source in this frequency band. So our observations actually show that there is a possible absorption process that is taking place here, and over different epochs we still see the absorption happening. Unfortunately, we didn't get detection, so we cannot give quantitative estimates of what the absorption is doing over there. But this again suggests that this source is actually in a very very dense environment. For the so yeah, if we just go back a few slides, we did see this this variation in the flux density itself. So for frequencies above 1.5 gigahertz, sorry, yeah, for frequencies above 1.5 gigahertz, there were already studies done on the variability itself, and there has been some evidence for variability in the 3 gigahertz. So what we did was we took only the 1.5 gigahertz data and we looked at the possible variability. So one of the possible reasons for a variation in the flux that we see is scintillation. So as we had already talked about, PRSs have as we have already talked about, PRSs are very small objects, so have a very compact size, and so they can actually have this thing called scintillation. So it's like a radio twinkling. From our observed data, we were able to calculate the modulation, and from the modulation, we can actually place. We don't get as much modulation as expected from scintillation in this direction, but we have tried fitting for the entire data, or also tried removing this this decay trend and looked at scintillation, and we are able to give some constraints like a conservative lower limit on the size of a scintillation screen that can be at different distances at like 0.1 kiloparsec, at 1 kiloparsec, or 10 kiloparsecs. And these lower limits sit within the limits that are already present, which was actually discussed in this this paper. So yeah, with that I'll just give a summary and I'll take any questions.
Thank you. Any questions, please? Ish.
You showed the GMRT upper limits.
Yes.
Could you point the 1 gigahertz point? Which ones would be like closer to the epochs? If one has to connect the spectrum.
Yes.
And these are multi-epoch points, right?
Yes. Yeah. So actually, so we had GMRT. So GMRT follow up from I think from here. So all of these points are GMRT 1.5 gigahertz.
Yeah, in the spectrum, I mean.
In the
next slide, yeah.
In the spectrum, it's slightly hard to see. So just a second. So I'll just go here. So 2 years since, this is 2.5 years since observation. So that is like 2021. So from the 2020 epochs, which have these points, the hexagonal points, all of these later at 1.5 gigahertz. So all of these at 1.5 gigahertz with the hexagon star, and these are the points.
Okay, the kind of steep turnover you see, is it still consistent with free absorption or synchrotron self-absorption?
Yeah, actually, I was trying to look at that, but the problem is that since we don't have actual detections, we cannot exactly say what this one is. We can maybe plot a slope for the free or the synchrotron self-absorption and check that. But yeah, quantitatively, I haven't estimated whether it is free or.
Hi, Arvind. So my question is regarding constraining the size of the PRS, and if that, what are the constraints we can put on different models based on that?
Yeah, so I mean, yes, once we constrain the size of the PRS, I guess we can say if it is the immediate vicinity. So I mean, there are estimates, at least for say these two models, there are estimates of the the size that this nebula can inflate to, the size that given module or the other parameters, you can get the size of this nebula or the size of the this cloud that it can this central object can inflate. And so if we get in similar sizes, if the constraints are agreeing with that, then we can make some statements about these models. So that was the idea.
So thank you, and I'm sure more questions we'll address during the break.